Welcome to Learning Management System, e-learning. In this video, I have to provide the proof of Cayley's theorem. It is very important theorem in permutation groups for semester 3 degree students. In group theory, Cayley's theorem, named in honor of Arthur Cayley, states that every group is isomorphic to a subgroup of a symmetric group. Subgroup of a symmetric group means permutation group. Let G be a non-empty set. A permutation of set G is a bisective function from G to G. Here domain is equal to codomain is equal to G. The set of all permutation of G forms a group under function composition called the symmetric group of G. Now let us move to our presentation. Cayley's theorem statement. Every finite group G is isomorphic to a permutation group G dash. Proof: let G be a finite group and A be an element in G. First, we define a mapping FA G to G as FA of x is equal to AX for all x belongs to G. G, domain, here domain is G and codomain is G. FA G to G is defined as FA of x is equal to AX for all x belongs to G. It is denoted by equation 1. First, we prove that FA is a permutation. Permutation means a bisective mapping on G is called a permutation. Bisective means 1-1 and onto mapping. First one 1-1 mapping. Suppose FA of x is equal to FA of y for all x y belongs to G. FA of x by definition, FA of x is AX. So AX is equal to FA of y is AY. AX is equal to AY gives x is equal to y. Clearly, FA of x is equal to FA of y gives x is equal to y. This means FA is 1-1. Second one, FA is onto mapping. Let y belongs to G. G is a codomain. By definition of onto mapping, every element in the codomain G having at least one pre-image element in the domain G. Since FA of x is equal to y, FA of x is equal to y, by definition using 1, FA of x is AX is equal to y. AX is equal to y, on both sides multiply with A inverse AX is equal to A inverse y. By using associative property, A inverse A into x is equal to A inverse y. By inverse property, since A belongs to G, A inverse also belongs to G. Since G is a group, by inverse property, A inverse is equal to A inverse A is equal to E, where E is the identity. By identity property, AE is equal to EA is equal to A. Here, A inverse A is E into x is equal to A inverse y. E into x means x. X is equal to A inverse y. Here, x is equal to A inverse y. For every y belongs to G, there exists an element x is equal to A inverse y belongs to G such that FA of x is equal to, by definition, using 1, FA of x is AX. So, FA of x is, here x is A inverse y, FA of A inverse y is a single element. This is A into A inverse y. So, this is A inverse into y by using associative property. A inverse is E into y is equal to y. So, FA of x is equal to y. FA of x is equal to y. So, this means FA is onto mapping. Every element in the codomain having pre-image element in the domain. So, therefore, FA is a bisective mapping. Since F is 1-1 and onto, F is a bisective, that means FA is a permutation on G. Let G dash equal to set of FA such that A belongs to G with the set of all permutations of G, since FA is a permutation. First, we prove that G dash is a group. Group means G satisfies 4 conditions: closure, associative, identity, and inverse. First one is closure. Take 2 permutations FA, FB belongs to G dash, where AB belongs to G. FA circle FB of X, the composition of mappings. Here binary operation is circle, composition of mappings. FA circle FB of X is equal to FA circle FB of X is FA of FB of X. Using 1, FA of X is equal to AX. Here FB of X is BX. So FA of FB of X is FA of BX. So FA of X, here FA of X is AX, this is A into BX. Using 1, A into BX by using associative property, AB into X. AB into X means AB, FA of AB into X, since FA of X is AX. That means circle is a binary operation in G dash. Here FA circle FB is equal to FAB. It is denoted by equation 2. So very, very important relation. FA circle FB equal to FAB. Second one is associative. Let FA, FB, FC belongs to G dash. Take 3 permutations in G dash where A, B, C are elements in G. Using 2, FA circle FB, circle FC is equal to FA circle FB is FAB, circle C, FC. Using 2, FAB circle FC means FABC. Using 2. FABC, ABC are elements in G by using associative property. FAB to FA into BC. FA into BC, that means FA circle FBC. This is FA circle FB circle FC using 2. So FA circle FB is equal to FAB using this very, very important result. So this operation circle is associative in G dash. Third one, identity. Take 2 permutations, FA, FB belongs to G dash where AB belongs to G. Let E be the identity element in G, since G is a group. By identity property, AE is equal to EA is equal to A for all A belongs to G. Now FA circle FE is equal to FAE. Using 2, FA circle FB is equal to FAB. Here FA circle FE is FAE, AE is equal to A, this is FA. And FE circle FA is equal to FEA. FA is FA. Therefore, FE is the identity in G dash. Fourth one is inverse. Take 2 permutations, FA, FB belongs to G dash where AB belongs to G. Since G is a group, every element in G having multiplicative inverse. A belongs to G gives A inverse belongs to G. So B belongs to G gives B inverse belongs to G. By inverse property, A inverse equal to A inverse A is equal to E, and B inverse is equal to B inverse B is equal to E, where E is the identity element. Now FA circle FA inverse is equal to, using 2, FAA inverse. FA inverse is FE. Again, FA inverse circle FA is equal to FA inverse A, using 2. A inverse A is FE. So FA circle FA inverse is equal to FA inverse circle FA is equal to FE, gives FE is the identity element in G dash, is a codomain. So FA inverse is the inverse element of FA in G dash. Clearly, G dash circle. This group is called the regular permutation group or symmetric group. Now we prove that G is isomorphic to a permutation group G dash. Since G is a group, given condition, that is G is isomorphic to G dash. 2 groups G and G dash are said to be isomorphic. First we define a mapping from G to G dash, which is 1, onto and homomorphism. Define a mapping pi G to G dash as pi of A is equal to FA. Here G is the finite set, elements A, B, C and so on. G dash is the permutation group. Permutation groups is the set of all permutations. So pi is FA FA, FB, FC. These are all permutations. So pi of A is equal to FA. It is denoted by equation 3. Now we prove that pi is an isomorphism. Isomorphism definition. Isomorphism means 1, 1, 1, 1, onto, and homomorphism. First one is pi is 1, 1 mapping. Let A comma B belongs to G. A and B are two elements in G, and pi of A is equal to pi of B. Since pi of A is equal to pi of B, by definition, using 3, pi of A is equal to FA. FA is equal to FB. That means FA of X is equal to FB of X for all X belongs to G. Since FA of X, using 1, FA of X is equal to AX for all X belongs to G. So FA of X is AX, FB of X is BX. So by using right cancellation law, A is equal to B. So pi of A is equal to pi of B gives A is equal to B, which means pi is 1, 1 mapping. Distinct elements in G having distinct images in G dash. Second one, onto. Pi is onto. Let FA belongs to G dash. G dash is the codomain. So FA belongs to. So every element in the codomain having at least one pre-image element in the domain G. So where A belongs to G, then pi of A is equal to FA. FA is a permutation in G dash. So which gives pi is an onto mapping. Pi of A is equal to FA. Third one, homomorphism. Let A comma B belongs to G. A and B are two elements in G. Now pi of AB is equal to pi of AB. Using 3, pi of A is FA. Pi of B is FB. Pi of AB equal to FAB. So using 2, FA circle FB is FAB. FA circle, FA means pi of A. Pi of A circle, pi of B. Here, operation in G is multiplication and operation in G dash is circle, composition of mappings. So that is pi of A dot B is equal to pi of A circle pi of B. This means pi is a homomorphism from G to G dash. Clearly pi is 1, 1 and onto and homomorphism from a group G into a group G dash. This means pi is an isomorphism from G to G dash. Pi is an isomorphism from G to G dash. This concludes that G and G dash are isomorphic groups. That means G is isomorphic to G dash. Hence proved.